Okay, let's look at another relative motion example. In this one, it says a plane engine can propel it at 150 meters per second. So that is our air velocity. The pilot wants to go due west, but there's a wind of 30 meters per second south. So that's our V wind. South and west. What direction should the pilot aim the plane, and what will its ground speed be? Okay, well, let's draw an equation. So he wants to head directly west. In reality, that is our V ground. The plane can fly any direction, and it can fly at 150 meters per second. And we know that there is a wind of 30 meters per second south. So let's draw our wind vector. It's going to be pointing south, and we know that will be 30 meters per second. Now we need to draw a air velocity so that our air velocity plus our wind vector will equal to our ground vector. So therefore, we need to draw something that starts from the tail of the ground vector, because that's our resultant, to the tail of our wind vector, because that is the second thing we're going to add. So this vector, the one we just drew in green, is our air velocity. And we know that is our 150 meters per second. The first part of the question, where should he aim the plane? We're looking for that angle. We have here a opposite length of the triangle and a hypotenuse length of the triangle. Therefore, we know the function we're going to use is inverse sine. So the inverse sine of 30 over 150, our angle here is 11.5 degrees. So the pilot should aim 11.5 degrees north of west. The second part example asks us what will its ground speed be. So we're looking for the numerical value for V ground. And because this is a right angle triangle, we can use Pythagoras' theorem to figure it out. However, in this case, our V ground will be the square root of our V air, which is 150 meters per second, the square of that, minus our wind velocity of 30 meters per second squared. Because we have the hypotenuse and we're subtracting it with the air velocity, and don't forget the square root. So our V ground here is 146.97 meters per second. Put into proper scientific notation with sig digs is 1.5 times 10 to the 2 meters per second. So there's only a very small difference in the velocity, but there is a noticeable difference. And lastly, it asks us how long will it take for him to travel 200 kilometers. And the hint there is, which velocity should you use? You should always use the velocity that is parallel to the displacement vector you are trying to determine. And because you're displacing 200 kilometers in this direction, in the west direction, you should be using the V ground velocity. So let's figure it out. Time equals distance divided by time. Distance is 200 kilometers, or 2.00 times 10 to the 5 meters, divided by our ground velocity of 146.97 meters per second. Remember to keep all the significant digits in your intermediate calculations. And the answer here is 1360.8 seconds, or 1.4 times 10 to the 3 seconds. Let's look at another relative motion example where there's a current or a wind involved. Here, a ship's captain wants to travel at 5 meters per second at 60 degrees RCS, but there's a current of 1.0 meters per second at 125 degrees RCS. Where should he aim the ship, and what speed does the engine need to give to the ship. So let's draw this out. We want to find at the end of the day a ground velocity of 5 meters per second. And it's at 6 degrees RCS, so this arrow should be pointing up and to the right. There's a current, however, of 1 meter per second at 125 degrees RCS. We should draw this one arrow up to the left because 125 degrees is up towards the left. And we'll label that our current velocity, 1.0 meter per second. We need to find an arrow that, when added with the red one, will give the blue one. And this is our sail velocity, or the velocity the engine must give to the boat. Again, the red one here is our current. The blue one here is our ground velocity. And we're looking for the green one. So it's clear that we must have a equation that states V ground equals V sail plus V current. Here we're looking for V sail. So to rearrange our equation, we have V sail equals V ground minus V current. And this minus will be very important when we set up our table. So let's set up our table. We have 5 meters per second at 60 degrees RCS minus 1 meters per second, 125 degrees RCS. And again, we're going to subtract. Because these two vectors are not linear, they're not on one dimension, and their angle, we need again to break it down to x and y components. For the x component, remember, it is the cosine function. And for the y component, it is the sine function. We use our calculator to find the difference, and it tells us the x component, the difference in the x component is 3.074 meters per second, and in the y component it is 4.355 meters per second. Now those are merely the x and y components of our sail velocity. We have to use Pythagoras' theorem to put it back together. We'll quickly draw a label diagram. Horizontally is 3.074, vertically is 4.355, and we're looking for the hypotenuse. The hypotenuse will be the square root of 3.074 squared plus 4.355 squared, and that is equal to 5.33 meters per second. We'll also need to find an angle. That angle there, again, we're going to use a tangent function because we have an opposite side and an adjacent side. It's the inverse tan of 4.355 divided by 3.074. Again, all in meters per second. And our angle here is 54.8 degrees. So our captain must have the engine provide the ship with 5.33 meters per second of velocity and aim his ship at 54.8 degrees RCS in order for that at the end of the day the boat to travel at 5 meters per second at 60 degrees RCS.